Time machine chart and standard work combination chart are used for improving a single process that involves both operators and machines. These methods are based on observations of the actual process or a video of the process and also on common sense. Users find a better sequence of steps in the process for reducing process cycle time. Some improvement opportunities may not be visible in these observation-based methods. We now demonstrate a scientific and powerful method that can easily improve cycle time further by finding the best sequence of steps. Let us consider a project that seeks improvement in standard work of a process. Suppose the process consists of 14 steps T1, T2, T3, and so on T14 as shown in this table. You can find estimated durations of steps in duration column and precedence relations among steps in predecessors column. This diagram shows precedence relations among steps graphically. The process involves an operator and a machine. Resource requirements column contains resource requirements of each step. Some steps need only the operator and some steps need only the machine. Some steps need both operator and machine. This table contains operator movement times between steps. After performing a step of the process, operator may take some time to move to the next step in the sequence. For example, if operator has to start step 60 after performing step 20, he needs 5 seconds. Cells in red color correspond to movements which will not occur due to precedence relations. Cells of gray color represent movements which take no time. Let us now schedule all steps as per the current standard work. This Gantt chart shows all steps of the process on a timeline. In this chart, green bars represent steps to be performed only by the operator. Blue bars represent steps to be performed jointly by the operator and the machine. Red bars represent steps to be performed only by the machine. Hashed bars represent operator movement times. In the top row, green bars represent steps to be performed by the operator with or without the machine. Hashed yellow bars represent movement times required by the operator. Yellow bars in the top row represent operator idle times. We can see precedence relations among steps can be seen by checking this box. Here is the current sequence of steps. Only T6 and T8 are non-critical steps in this shtull. Let us now see improvement opportunities in the process only with observations. There are 2 intervals in which machine is busy and operator is idle. Let us exploit them. Let us drag step T2 into the first idle period. Now the sequence changed, the first idle period vanished and process cycle time is reduced from 148 to 135. If there is no improvement, we can undo the drag. Let us restore the advantageous change in the sequence. This is the sequence of steps now. Here are the non-critical steps. Look at this operator idle time. Can we improve cycle time by removing this idle time? Let us now drag T3 to the idle period. Note that process cycle time has reduced further from 135 to 120. The effects of both changes can be seen in this table. Here is the new sequence of steps. Here are the critical steps. Note that it is not easy to identify any more potential improvement opportunities only with observations. Let us optimize the sequence of steps using a schedule optimization algorithm. This is an optimal sequence of steps. It reduces cycle time further from 120 to 106. Here is the new sequence of steps. Here are the critical steps. This chart can be taken as man-machine chart. Machine has some intermediary idle time. An operator has no idle time.